All right. So this is our continuation of our center of mass stuff, our lesson. Right. So we talked about how to find the center of mass in the square thing. We talked about how to do it in the subtract thing, um, or the non-symmetric thing. Right. Now we're going to talk about what we can do with this information. So first is to use it for the tipping slash balance point information. Like, if you know where it tips, you know where it balances, you can use that situation. You can use it to find that situation, or you can use it to once you have that information, you can use it to find something else. You can also use it to internal reconfiguration. So what I mean by that is if two objects rearrange them, like you have one object that's like made of parts that can like shift, right? So a very simple example we do later is like somebody's in a canoe, right? They walk across the canoe moves the other way. Okay, that's what I mean by reconfiguring. That Newton's third law says that the force is the same. The force in each of them, right, equal and opposite. So, the mass of one times acceleration of other is equal to negative mass of two times acceleration of the second one, which means that the velocities have to interact, which means the displacements have to interact, right? And we actually get this mass one x1 is equal to negative mass two. Oops, that should be an x2. Okay. This right here is actually not totally true. It's actually, this is if it starts at rest. This should really be, if we want to be super technical here, this should really be the delta, right? I don't want it to be subscript. Right, it's the delta, right? Just because of the, right, because it's all about, like, velocity times time, or the integral of velocity is always going to give you delta x, right? So there's that. Okay, so we end up in that situation. All right, so let me do some quick examples here of how to use those different things. So our first one is a what's it called? A tipping point problem here. We've got a cat walking along a 2x4. So let me draw it out here for you. Okay. We got these, like, you guys know what sawhorses are, I hope. They're like the little things you rest boards on so that they can be sawed. Okay, I hope that's what you know what they are. Okay, there's a sawhorse, there's my beam. It's not a very good one. The cat is walking. The cat's going this way. And at some point it tips. Okay? So, we know what tipping point is, right? So we know that the center of mass, the tipping point is right here. This is the tipping point. We've also been told that that is 2 meters from the left end. Okay? Or 1 meter from the from the right end, right? It's 1 meter from the right end, technically. I decided I was going to measure everything from the left end. I don't know why I did that, but it doesn't really matter as long as you're consistent. Okay, so we've got, and we know the cat gets all the way out till it is 0.25 meters. So, I know the center of mass equation, right, is x center of mass times m total is equal to m1 x1 plus m2 x2. X center of mass is 2 from the left end. The total mass is, right, the cat plus the mass of the beam. It's our unknown. M1, let's make that the cat. So 8 times location of the cat. I'm going to call it 2.75 because, again, I'm measuring from the left end. You can measure from the right end just as well. Honestly, it might be a little bit simpler math-wise. Plus, right, then we have the mass of the beam, which we don't know. That's M. And the center, and where's the location of the beam? Well, we're measuring from the left end, and the beam is symmetric, so we can say that it's at the middle, so 1.5. Okay? Now we solve. 16 plus 2m equals, what does that come out to be? 22. Plus 1.5m. What was this? 0.5 equals 12, or equals 6. Not 16. Equals 6. Actually, I need an m there. 5m equals 6, right? So that means that m equals 12 kilograms. Okay? So you can use it to solve for a mass. I know that's what we could have done, right, with the ruler in class today, right? If I at 10 1/4 inches, like we knew the mass of the other one was 100 grams, etc. All right, here's the separation thing. So basically, what we've got here is we've got this setup where we've got a dock, then we've got water, and we've got a canoe. We got a person in it. And the person's going to move this way. When they move that way, the canoe moves back the other way. Oops, the person's not on that side anymore. They're on the close side. Right, so this is 2 meters. This is 3 meters. We don't know what this is. This is X. But I do know that this is still 3 meters. Okay, the point here is that because there's only internal forces, okay? If the only forces are internal, in other words, if the person is pushing against the boat and the boat's pushing against the person, there's no other forces, and again, we think of the water business as being pretty limited, then the center of mass actually stays the same. Okay. All right. So, what does that mean? It means X center of mass 1 initial equals X center of mass final. All right. So X center of mass, right? That is X1 or M1 X1 initial. I'm not going to write all the subscripts. That's really annoying. Divided by M1 plus M2 is equal to M1, M2, or no, it's M1. M1, X1, M2, X2. These are all finals over M1 plus M2. This is all final. This is all initial. Now you'll notice right here, right, that the denominator cancels right out. Okay, and that's going to happen every time you do one of these ones, right? This were like internal reconfiguration. Denominator cancels out. That's convenient. So I'm going to say M1, right? That's my person. Let's say that's 75 kilograms, and their location is I'm going to measure from the dock, 5 meters. And the canoe is 50 kilograms, and it is located right the center of it, right? This is where the center of mass is, right there, and the center of that is exactly 3.5 meters from the dock. That's equal to, on the other side, the person is now X from the dock, and the canoe is X plus 1.5. Right? So we've got 50 times X plus 1.5. This is 375 plus 175 is equal to 75x plus 50, right? Plus, or 50x plus 75. I get 475 on this side is equal to 125x. X is equal to 3.8 meters. Okay, so you moved only about 1.2 meters, right? Because you started out 5 meters and now you're 3.8 meters from it. So the canoe moved a little further than you did, which makes sense, right? The canoe's lighter than you. All right, this one's a little tricky because this is a problem you could easily be doing without center of mass. It is slightly easier to do it with center of mass than it is without center of mass. Okay, so this is a similar problem, except in this case it starts out moving, right? We got an object that's moving and it separates. Again, an internal reconfiguration. Okay, now what that means is that the X center of mass is that the X center of mass keeps moving. And the center of mass, where the center of mass would have been if they hadn't separated, right? No separation is equal to the X center of mass separation. Okay? this is both at 3 seconds. So at 3 seconds. This is true. Okay. So there's a center of mass with no separation. Well, that's easy, right? They were going along at 10 meters per second and 3 seconds, so it's 30. Right? The separation has to be 30. So it's going to be x1 m1 plus x2 m2 all over m1 plus m2. Right? So 30 equals x1 is at 10 times 5 plus 10 we'll make it x, which is the unknown location, times 10 all divided by 15. And I can solve for x. X ends up equaling 40 meters. Okay. Now, you could have done this with momentum, separation, everything like that, and then kinematics, but it probably would have taken you more effort than just knowing that the center of mass and how the center of mass is moving is unchanged by them separating, as long as it's only internal forces.